Assalamu alaikum warahmatullahi wabarakatuh, and very good morning to my examiners, Associate Professor Dr. Muhammad bin Mansour and Dr. Afaru Razi bin Abu Bakr, and to my chairman, Dr. Siti Amali, and Assistant Chairman, Inche Suhaimi. Today I'm going to be presenting uh, my Viva thesis under the title of Investigating the Effect of Humidity and Temperature for LCL Compensation Wireless Power Transfer. I am Ismail Ahmad Mahdi, and my supervisor is Dr. Jabbar Al Fattah bin Yahya. This is going to be the content of the presentation. We are going to start from introduction, problem statement, objective scopes, and literature review, methodology, result and discussion, and then we finish by conclusion and recommendation. Okay, so wireless power transfer have been introduced in the past few decades by the scientist Nikola Tesla. Uh, the benefit of wireless power transfer is basically to transmit power from the primary to the secondary or from the source to the load without any mechanical contact. Wireless power transfer has a variety of methods that have been invented, and the table here shows some of the methods that are being used in wireless power transfer. For example, they can be categorized into two categories: far field and near field. So the far field, normally from the name, it normally for a long range, and the near field is for short distance. The far field mostly use couple mode theory, the near field use induction theory, and the frequency for far field is mostly high because of the distance, and near field mostly use low frequency, and the efficiency higher in near field and low in far field. So now we move to the problem statement. To ensure the capability of energy transfer at longer distance, the resonant coupling must depend on the rate determined by the gain bandwidth or the quality factor. Quality factor is a very important things we need to consider when designing a wireless power transfer. Insufficient Q factor means result in weak coupling or possibly loss of energy. Low power factor means high loss of energy, and too much Q factor would result in resonant coil being very sensitive to its surroundings, such as temperature and humidity. So temperature and humidity actually have has impact, as we know, to the conventional method, uh, such as the normal wiring charging. They are very important factor to consider when designing any electronic appliances. So the wireless power transfer basically use magnetic field to transfer from the source to the load. So there is a distance between the source to the load, and that distance might be affected by the surroundings, such as temperature and humidity, which might lead to increase or decrement of the magnetic field that's being transferred. Also, wireless power transfer poses a high risk for human and animal, as I mentioned. They have distance between from the primary to the secondary, and it might cause health problem. So this study aims to model and design a wireless power transfer system that can transmit energy from the transmitter to the receiver, and to investigate the effect of temperature and humidity on wireless power transfer, and also study the safety risk for the electromagnetic exposure on the system to the general public. So here we have four objectives: to design and model wireless power transfer using software, using Gemma Designer, to analyze the effect of load and input voltage on the efficiency of the system, to investigate the effect of temperature and humidity in WPT, and to study the safety of electromagnetic limits based on a specific absorption rate. This project aims to design wireless power transfer that can transfer medium to low voltage, which is maximum of 200 volts. The frequency used in here is from 10 to 20 kilohertz. The air gap used is from 0 to 100 millimeter or 10 cm. And then the software design used is JMAC Designer. The prototype is focusing on the transmitter and receiver part. The study of the electromagnetic exposure based on ICNI RP standard for the safety, magnetic field safety consideration, and the temperature and humidity are only performed on the experiment due to the lack of the prototype. Only on the experiment due to the lack of the parameter in the software. literature review. So now we see the classification of wireless power transfer. Basically, wireless power transfer has so many classes. None, as I mentioned earlier, near field and far field, or also they are called non-radiative and radiative field. So the near field has two types: coupling coil and inductive coil. The coupling coil use capacitive coil or capacitive plates to transfer from the primary to secondary, and the inductive coil use induction coil to transfer from the primary to secondary. As for the far field, mostly they use microwave and laser. So this is basically the block diagram of wireless power transfer, the simple representation of any basic wireless power transfer. We have DC source, and then we have inverter circuit which transfer from DC to high frequency AC, and then we have primary compensation topology, and then we have primary coil. Then here is the secondary side. We have the receiver coil, and then we have secondary compensation, and then we have rectifier to transfer from AC to DC and then to the load. Okay, basic compensation topology. So as we have seen just now in the block diagram, the compensation, there are four types of compensation topology, which are series, parallel series, and parallel. So the advantage of compensation topology is basically to make the system resonant, which means the frequency in the primary is same as the frequency in the secondary, which we would be able to get the maximum efficiency. Also, it minimizes the volt amp of the power supply and regulate the current value in the supply loop and voltage receiving loop with a high frequency. These are the representation of the basic compensation topology. We have series parallel, and then parallel series and parallel. Beside the basic compensation topology, we have advanced compensation topology. So the advanced compensation topology are double-sided inductor capacitor inductor, and then double-sided inductor capacitor, or LCL and LCC. So LCC compensation topology was developed to provide more flexible operation in the control system by tuning the characteristic of the compensation network. That's why in this study we are going to be using LCL because it has large resonant capacity and less device pressure and frequency stability as well. So the impedance transformation characteristic of LCL topology make the resonant capacitor obtain high voltage. Moreover, the LCL topology increase the total reactive power. So these two circuits shows the basic circuit diagram of LCL and CLC compensation topology. So now we move to the methodology. Basically here for the methodology we have three parts divided into three. First, we design and simulate the wireless power transfer in JMAC Designer, and then based on the simulation, we design the prototype, and then after the prototype is complete, then we compare the simulation and the prototype result. So this is the flowchart of the methodology for the hardware design, and so we can see here from the start we generate the PWM, and then we have high frequency inverter design, and then if you can get the high frequency AC signal, then we move to the coupling coil. If not, then we troubleshoot and redo it again, and then from the coupling coil compensation topology, and then to the plates, primary and secondary plates. If everything goes to the plan, then we move to the secondary compensation topology. If not, then we troubleshoot again the coupling coil, and then after the compensation topology is done, then we test the effect of temperature and humidity, and that's the end of the project. Yeah, so and this is the PWM, how we supposed to generate the PWM. Normally here we use a CCS code generator or code composer studio, and then we fed the frequency and duty cycle, debug it to the TI board, Texas Instrument board, and then to the MOSFET inverter for switches MOSFET inverter. So this is the block diagram of the system. So we have the DC supply, and then we have a filter here, capacitive filter, and we have a high frequency full bridge inverter for switches, and then this is the control path. We have the gate driver, and then we have This one is the external source to generate to operate the gate driver, 5 volt. And then this is the code composer studio, and this is the CCS. I mean, this is the Texas Instrument, and this is the code composer studio. So we debug the system, the code into the board, and then from the board to the gate driver, and then from the gate driver to the switches. So that's how we get the high frequency AC signal in here. And then from here it goes to the compensation topology. These are the compensation topology, inductor, capacitor, and then uh, to the primary plates, and then from here to the secondary. This is the air gap from here, as we can see from this picture. This is the primary and this is the secondary. So, and then this is the secondary coil, and then we have the secondary compensation topology, these tools, and then to the rectifier for the switch rectifier, and then to the filter, and to the load, resistive load. This is basically the system. So now we move to the result. As mentioned earlier, we have two type of result: simulation and experiment. So these are the parameter for the result. We have the parameter in here, and then this is the result of this system. Here in the software, I use uh, two type of designs with this one and this one. This one we call it ferrite sheet core, and this one is ferrite spool core. Basically, the difference is this one is the core is like a sheet, which or it cover all the coil from outside, and this one is just the core is cover some part of the ferrite of the coil to see which one is better. So this is the result obtained, the effect of load resistor on the system. Basically, we see the effect of R load to the system, and then here we can see the blue one is the sheet core, and this one is the spook core. So as we can see, as the resistive load increase, means the efficiency of the system also increase. We can see here from when R is only 10 ohm, the system efficiency for the sheet is just around 50%, and for the spool core is just around 25%. And when the R is around 80 ohms, you can see here the system is around 90 something, 92 or 93% efficiency, which is higher. And for the spool core is around 61% efficiency. And this is the effect of DC input voltage on the system. So as we can see from the two graph, this one is for the flat sheet and this one is for the ferrite spoke. So as the DC input voltage, as we increase the voltage, we can see the efficiency of the system remain constant. That means the increment of the voltage does not affect the efficiency of the system for both designs. As for the distance, we can see here this one is for the sheet and this one is for the spoke core. So we can see the distance is, when the distance is around just 2, the efficiency is very high. This one is 2 cm. The efficiency is very high, it's almost 90 something percent. And then as the distance increase, the efficiency reduces to, at 10 cm, the efficiency reduces to just around 80%. Sorry, around 70 something percent. And the same applies here. As the distance increase, the efficiency drops to just around 60%. So this is the comparison between the two systems, the flat sheet and the ferrite spoke. Normally we look at the efficiency because this is what we mostly focus about. So here we take input voltage as a 10 volt, and then we measure the output voltage as well as the output power and input power, and then we compare to the distance. So as we can see, as distance is 2 cm, the efficiency is like 95%, and when the distance is like 10 cm, the efficiency drops to 71%. As for the spook core, you can see the efficiency here dropped to just 63% at 10 cm and 94% at 2 cm. So from these results, we can conclude that the ferrite sheet core is better and have high efficiency than the spook core, which will be used in the experiment. So now we move to the experimental result, and then we can see here this is the parameters for the experiment. We use the input voltage as 50 volts, and then we have the primary and secondary inductance, primary and secondary resistance, the winding resistance, and the primary and secondary compensation capacitor. And then we have the distance is around maximum is 10 cm. So this is the setup of the system, and then you can see here this is the high frequency inverter, and this is the gate driver, this is the TI board, and here this is the compensation capacitors, and this is the main DC source, this is the external DC source, and the oscilloscope to see the result. And then we have here resistive load, uh, 3 resistive loads, and we have here primary and secondary the primary and secondary coil, and this one on top is the core material. And then here we have the secondary compensation capacitors, and then we have the rectifier, we have the capacity filter, and then to the load, these are the loads. So first we check which frequency would be to at which frequency we will have a higher efficiency, and then we test different frequency from 15 to 21 kilohertz, and then we notice that at around 17.8 we get around 69.9, around 70% efficiency, which is the highest. So this one will be used as the resonant frequency for the system. So here as well we test the effect of load on the system, and then we can see here at the load resistor increase, and the efficiency also increase until when it reaches to around 80 ohm, then it doesn't increase anymore, it drops slightly and then remain constant, and that's because of the Q factor. And same goes for the current. As the load increase, the input current always increase, but the output current like slightly decrease as the load increase because the voltage increase. So here we also test the effect of DC input voltage on the system, and then we can see here this one is the input voltage versus the efficiency. We can see the input voltage is almost constant, so there is no change. It doesn't matter if the voltage is 10 or 50, the efficiency is going to be almost same. And we did the same thing when the input voltage and at different resistive values, and we can see almost the efficiency is constant. And the resistor value, as we mentioned earlier, when the RL here is around 85 means the efficiency is higher. When the RL is around 30 means the efficiency is like lower. And this is the result on the oscilloscope. So this is the PWM, these two are the signal, the input and the positive and negative signal for switch 1 and 4, and this one is for switch 2 and 3. And this is the primary coil signal, and this is the secondary coil signal, the voltage when the voltage is at 10 volts. Same here, when we increase the voltage to 50, we can see the signal increased, and the primary and secondary signal increased. So here we test the coil to coil efficiency, means we just test the AC part from the AC to the AC, and then we found out that the distance, the efficiency is even higher. At 2 cm the distance, the efficiency is around 91%, and at 10 cm the efficiency is around around 68%. And so this is the temperature setup, how we connect the temperature. Basically I made that this box, and then there will be the plates, the primary and secondary from the bottom and top, and then we have this one is the sensor to measure the temperature and humidity. This one is the sensor, which is this one, to measure the temperature and humidity. And then here I use this one to generate the temperature and humidity, connected using aluminum foil. And then here I have exhaust fan to like to take out the extra. If I don't want, if the temperature is too high, I will open the exhaust fan for it to cool down, and then I'll open that, I will close to get the temperature needed, and then take the reading using this sensor. So basically that's how I measure the temperature and humidity. So this table is obtained as we test the temperature and humidity, and we can see that the efficiency as the temperature increase from 28 degrees Celsius, which is room temperature, to 60 degrees Celsius, and humidity from 54 degrees Celsius, which is room temperature, to 99%. Sorry. The efficiency is almost same. There is no big change actually in the efficiency itself. as the temperature and humidity increased. So the input voltage was set at around 100 volt. I mean the input power was around 100 watt, and we get the output power is also around 66 watt. Yeah. So this one is the safety of electromagnetic based on the SAR, the magnetic field, and the input voltage. As the input voltage increase, the magnetic field also increase. But the magnetic field here is below the standard limit, so it's still safer for the human and the animal. And this is the comparison between the simulation and experiment. We can see that the simulation is like a little bit higher compared to the experiment for the efficiency, and also the distance. The simulation has better output result than the efficiency. And this one is also the table showing the simulation and experiment. You can see the efficiency for the simulation is like around 95%, whereas the experiment is just 91% when the distance is 2 cm, and just the distance is just 66, and here is 68 when the distance is 10 cm. So now we go to the conclusion. From the simulation result obtained, it can be concluded that the efficiency of the system was found to be around 72% at 10 cm distance and 94% at 2 cm distance between the coupling coil, and 17 at around 17 kilohertz efficiency. Also, the experiment result obtained that the efficiency of the system is around 92% at 2 cm and 67% at 10 cm. The resistive load has slightly effect on the efficiency of the system. As the load increases, the efficiency increases as well till it reaches a certain level at a certain point, which is at 85 ohms, and then it remains constant. That's because of the Q factor. So the result also shows that when the distance of the resistive load increase, only the output voltage value changes and the current remain approximately constant. So because as we increase the resistance, only the voltage value change. The temperature taken was from room temperature, which is around 25 degrees Celsius, at around 60 degrees Celsius, and humidity from 50 around 60 to 99%. And the result doesn't show any difference. Actually, there is no much effect. The temperature and humidity, they do not have much effect on the wireless power transfer. Yeah, and also the magnetic field distribution of the two design satisfy the ICNR IP guideline for the standard of high magnetic exposure for the general public. So these are the few basic recommendations for the system. First one is to improve the system efficiency. The efficiency is always the main issue for wireless power transfer, and use a high efficiency inverter. Sometimes the inverter also, the switches used in the inverter, they might have effect, so better switches is high efficiency for the inverter. And also design wireless power transfer suitable for high voltage application. Just now we designed for low voltage. And the effect of magnetic field is very important factor to be considered also. Yes. And that's all. Thank you very much for your time, and yeah, hope to see you soon.